In order to understand bearings and their application in the world of pumps, it's best to consider some of the fundamentals and terminology of bearings. Pump bearings have two general classifications: sleeve bearings and rolling element bearings. The sleeve bearing is used mostly on reciprocating rods and shafts and on some low RPM rotating shafts. For rotating and centrifugal pump shafts, the rolling element bearings have almost displaced the older sleeve-type bearings. The precision rolling element bearing may have round balls or rollers in the form of spindles, cones, or needles rollers as the rolling elements. The rolling elements move within an inner ring or race and an outer ring or race. Take a look at the following ball bearings. So the rolling element in this case is some ball bearings as depicted in the figure. These rolling elements move within an inner ring that you can see here and an outer ring or race that you can see here. The ball bearings are kept within the bearing using a cage as depicted here. And here you can see another example of an exploded view of a typical ball bearing, also called anti-friction bearing. Now let's see where these bearings are located in a centrifugal pump. The bearings are actually situated in these levels here, and with the cross-section of the pump you can easily identify them because you can see here the rolling elements or the ball elements. With centrifugal pumps, the outer race that you can see here in red is stationary and is seated into a bore in the bearing housing. And the inner ring that you can see here in green mounts onto, centers and rotates with the spinning shaft. This arrangement may be of course reversed in some special duty pumps. Now let's see a 3D animation of a pump in service just to reinforce the understanding. What you can see here is a cross-section of a typical centrifugal pump in service. So here you can see the suction side of the pump, the discharge side, the volute, the impeller, which is in our case here a closed impeller, the rotating shaft, and here you can see the ball bearings, also called anti-friction bearings. Now let's zoom in and take a close look at the bearings. So here you have the rotating shaft, the rolling elements or the ball bearings, the cage, the inner ring and the outer ring. And here is the bearing in animation. In the beginning of this video, I showed you some typical examples of ball bearings. Now let's go briefly through each one of them and see its main characteristics. We begin with the first type called Conrad Deep Groove. This is a single row bearing and it can handle moderate radial and axial loads from any direction. The second type is called double row not self-aligning. These bearings have two rows of balls and can handle 50% more radial load than the Conrad type bearing. Alignment for these bearings is very critical. Next we have the double row self-aligning bearing. These bearings have two rows of balls and they can handle some shaft misalignment. The axial or thrust loading is limited. Next we have the angular contact ball bearings. These are single row ball bearings capable of handling extreme axial loads in one single direction only. For this reason, in general, they are mounted in pairs to handle any opposite axial loads. Then we have the cylindrical roller bearings, which are bearings that are best suited to handle radial loads. It doesn't work well with axial loads. And these types of bearing are popular in electric motors. Next, we have the conical roller bearing. These bearings are good handling extreme axial loads in one single direction only. Then we have the needle bearings, which are a type of roller bearing with a roller diameter normally less than 0.250 inch and about a 1:6 diameter to length ratio, therefore the term needle. And finally you have the spherical symmetrical roller bearing. These spherical rollers are barrel-shaped and mounted in two rows rolling inside a common inner and outer race housing. Each type of these bearings is manufactured with different classifications of play or internal tolerance. This play or tolerance refers to the distance between the surface of the balls or the rollers and the internal and external raceways with axial or radial movement. The bearing tolerance is rated with the codes C1, C2, C3, C4, C5, and CN. The CN code is the normal, standard, or average precision. The C1 code is the most precise tolerance bearing, so the tightest bearing. And the C5 code is the least precision tolerance bearing, so the loosest bearing. A bearing without a stated code is normally a CN rating. Standard pump bearings are mostly C3 or higher, slightly forgiving and loose. With this understanding of pump bearings, you can see that it is not convenient to replace a C3 pump bearing with a C1 bearing. Because of its strict tolerance, a C1 bearing can handle less thermal expansion and lubricant contamination that occur with normal pump operation. A C1 bearing is less forgiving with thermal expansion and contamination and will fail prematurely. As we have seen in previous sections, the pump has basic head and flow specifications. The pump manufacturer installs bearings suited to the pump's design and general utilization. Based on this logistics, it's always best to use and replace the same type of bearing in a maintenance function. Oil is a popular pump bearing lubricating fluid. There are two classifications of lubricating oils: synthetic-based and petroleum-based. Synthetic lube oils were developed to improve their high temperature stability and overall temperature range. Petroleum oils are lower in cost and have excellent lubricating properties. Animal and vegetable-based lube oils are rarely considered for bearings because they deteriorate, spoil, and form corrosive acids. As a lubricating fluid, lube oil can be circulated, filtered, cooled, heated, pumped, or atomized. For these reasons, it's more versatile than grease. It is convenient in severe applications involving extreme temperatures and high velocities. The oil level and flow through high-speed bearings is critical, and these parameters should be monitored appropriately. Because oil is a liquid, it is more difficult to seal and contain inside the bearing chamber than grease. Viscosity is the term used to indicate the thickness of the oil or its consistency. The viscosity test is a measure of the film strength of the fluid. Excessive viscosity can lead to the rolling elements skidding inside the bearing races. This leads to raceway damage and overheating of the oil. Inadequate oil viscosity can lead to premature bearing seizure from metal-to-metal contact. Other properties to consider in selecting and using oil are corrosion protection additives, the pour point, the flash point, the viscosity index, carbon residue, and the neutralization number. Consider the loads imposed and operating temperatures of the bearings when selecting the oil and its viscosity. Correct selection is essential for long bearing life. The lubricant manufacturer publish a data sheet detailing the characteristics of their products. You should get this sheet study and understand the properties of the lube oil you're considering for use in your pump bearings. There are many advantages associated with lubricating oil. Among them, we can list the following. So, an excellent friction reduction at high speeds, good lubrication at very high or low temperatures, good stability, and good heat transfer. There are unfortunately some disadvantages to using oil. Among them, we can list the following. First, it is difficult to seal and retain inside the bearing chamber, requiring frequent refilling. Also, oil levels must be checked with more frequency as the temperature rises. And as the temperature rises, the viscosity of the oil will decrease, which will lead to more leaks. Now, if you combine petroleum oil or synthetic oil with a suitable thickening agent, you will get grease. The thickening agent can represent between 3% and 30% of the total volume of grease. The amount of thickening agent and the oil's viscosity will determine the consistency or stiffness of the grease. For general industrial service, popular thickening agent used to make grease are soaps of calcium, sodium, aluminum and lithium, and combinations of these. All greases have certain characteristics, but they should not be categorized for usage according to the thickening agent. For example, just because grease is thickened with sodium soap doesn't mean it is necessarily best in a particular service. No particular grease can satisfy all requirements, although considerable effort has been invested in developing a multi-purpose lubricant. Grease is selected for use in pump bearing for its advantages, including its resistance to dripping and running, and it's easy to seal and retain in the bearings. Grease also has some disadvantages. It is subject to separation and oxygen decomposition. It is difficult to clean and remove old grease from the bearing assembly. Now, let's talk about bearing lubrication in pumps. The majority of industrial pumps are designed with a horizontal shaft assembly, as depicted in the following figure. So, more pump bearings are lubricated with oil contained in the bearing chamber, which is highlighted here. Grease is preferred for bearings on vertical pump shafts. Lip seals, labyrinth seals, or mechanical seals are used to seal the bearing housing where the spinning shaft passes through, to keep any contamination out of the bearings and holding the lubricant into the housing. Bearing seals will be discussed later on in this section. Now, correct oil level is very critical. As a general guideline, the oil level should be halfway up the lowest ball or roller in the bearing assembly, as you can see here. And here you can see how the oil is injected into the bearing housing. Now, too much or too little oil will lead to premature bearing failure, which leads to coupling and motor failure on the power end and mechanical seal failure on the wet end. Oil mist systems exist to provide continuous and precise quantities of oil fog to the rolling assembly. These systems normally employ an additional pump, an atomizer, and a filter. These systems are gaining popularity in hot applications or with heavy thrust and radial loading. The oil fog is sprayed into the bearing chamber with either a wet sump or a dry sump. The wet sump method provides the bearings with a bath and a fog spray. The liquid oil or the bath is contained in an external lube bottle, as depicted here, and the oil level is halfway up the lowest ball or roller in the bearing assembly. The fog spray is contained in the bearing chamber overhead the liquid oil level. The dry sump method of oil misting has no liquid oil contained in the bearing chamber, but instead the entire chamber is filled with the atomized oil fog, as depicted in the figure. Both the dry sump and wet sump method of oil misting have a slight positive pressure in the bearing housing. This prevents contaminant and even humid air from entering the bearing chamber. Pump operators and pumping systems are plagued by uninspected premature bearing failures. Even if the cost of the bearing is small, the direct and indirect associated costs of its failure and replacement can be substantial. For example, a pump bearing may only cost $20 to buy, but its failure could also take out a mechanical seal. Now, besides the cost of the bearing and the mechanical seal, is the cost of disassembly and reassembly of the pump. And there will be other replacement parts to change, although they may or may not have failed. Some of these would be the casing gaskets, the pipe flange gaskets, the wear bands, nuts and bolts, not to mention the oil or grease lost. Then there is the time dedicated to the repair, which is also the time lost from production. Most often, the bearing or the lubricant is blamed for the failure. This is like blaming the fuse for an electrical failure. The failure is most likely a result of some abnormal operating condition or lack of proper maintenance. In short, something causes the bearing to fail prematurely. Among the most common causes of premature bearing failure are the following. First, improper mounting. Improper procedure when mounting the bearing on the shaft is one of the most common causes of premature failure. Roller bearings and ball bearings are precision devices, and correct installation practices are very important. They must be stored correctly and handled correctly to give good service life. The shaft and housing dimensions must be within limits specified by the bearing manufacturer. Shaft to motor alignment is also critical. You should strictly follow correct and acceptable practices when removing the old bearing and installing the new one. Cleanliness is the order of the day. You'll need a clean work area, clean hands, and cleaning cloths without fuzz, lint, or strings. So much of premature bearing failure is the direct result of not observing these basic concepts. The second common cause of premature bearing failure is vibration brinelling. Maintenance people are not normally familiar with vibration brinelling. The brinel marks themselves are small and even invisible indentions in the bearing raceway, as depicted in the following example. These brinel marks result from vibrations or shocks originating outside the bearing. Common sources would be cavitation, bent shafts, imbalanced rotary assemblies, and shock thrust loads. These vibrations cause the balls and rollers to jam into the raceways, causing the imperceptible indentations. The races eventually take on the appearance of a washboard effect. It is like driving a car at high speed over a rough roadway. The surfaces of the balls and rollers begin breaking away, therefore destroying the bearing. All bearings coming out of service should be disassembled to examine the internal rotary and stationary surfaces. Next, the third common cause is dirt and abrasion. Careless handling during storage and assembly damages a lot of bearings and lets dirt get in. Dirt, sand, and dust contamination between the balls and races of a new bearing can start a round of false brinelling, ruining the bearing even before it goes into service. Dirty, sweaty hands, damp cloths, humid air, and even the morning dew can start a rusting process that will destroy a new bearing. Bearings should be kept clean. Some studies indicate that more than 90% of all bearing failure is attributable to abrasive dirt entering the bearing before and during its installation. A grain of dirt or sand trapped between the ball and race of a precision bearing has the same effect as running a race with a rock stuck in your shoe. Sleeve bearings on some older, slower, larger pump shafts can withstand dirt contamination better than ball and roller bearings. This is because the tolerances are not so strict with sleeve bearings. The surface area of contact is greater, and the lubricant flushing action is better. The sleeve bearing material of construction is normally softer than the shaft material, and abrasives can be embedded into the bearing material without destroying it. This is certainly not the case with precision ball bearings. Now here's some guidelines to avoid bearing failure due to dirt and abrasion. First, never leave a bearing exposed overnight. If you want to store your bearings, then coat them with clean oil and cover them with clean oil or wax paper. Before installing the bearing, clean the internal bearing housing and shaft seat. Clean and paint all in-machined internal surfaces inside the bearing housing with oil-resistant paint. And finally, do never spin a new bearing by hand or with compressed air. This introduces dirt and causes it to embed into the protective grease. The next common cause is inadequate lubrication. Inadequate means not enough lubricant, and it also means the wrong type of lubricant. If the lubrication is insufficient, the bearing suffers short life from too much friction, high heat, and metal-to-metal contact between rolling and stationary elements. For horizontal shafts, the propel oil level is halfway up the lowest ball or roller in the bearing assembly, as depicted in the following figure. Some pumps have a site-level indicator showing the oil level inside the bearing chamber. It is recommended that you install these indicators if your pump don't have them. Teach the operators and mechanics to pay attention to the indicators. As for greases, lithium-based grease is for pump. Polyurea-based grease is for electric motors. If these two greases are mixed or confused, it will lead to premature pump bearing failure. Finally, the last common cause is excessive lubrication. Too much lubrication is as damaging to bearings as insufficient lubrication. It also leads to overheating. When the oil level is too high, the bearing bolts and rollers crush into the oil, pulling in air and bubbles, leading to foaming. The foam and froth mixed with air cannot remove the heat. The foam and froth in the bearing oil increases the volume and artificially raises the oil level, which leaks through the seals. When enough has leaked to stop foaming, the air bubbles leave the oil, resulting in inadequate oil levels. Too much friction heat and failure is the result.